Hello colleagues. Today we will be talking about fast indoor positioning system for quick sports, quick industrial applications and machinery, quick drones. Of course, it's still about precise indoor positioning system, but the focus is on fast moving objects and high update rate and the ways how to achieve it. What's the problem? If you have a typical update rate of 8 Hz, for very quick moving object, it may be simply not enough because you will have too few location points per movement. And instead of smooth track, you will have just sparse dots. What are the options? Well, two options. Either you slow the movement, which is typically not possible, or you increase the update rate. A regular way to increase the update rate we have shown already on our page, please check it. Basically, it's about reducing the size of their submap, if possible. So, because our typical and default is 30 meters, and if you have just 5 meters, you can increase the update rate significantly, basically 6 times. It's about increasing their radio profile, because in some cases radio may be the limiting factor, and reducing all kind of averaging, all kind of additional algorithms that can increase their latency, more or less. They do not decrease the update rate. But those typical cases we have discussed there, when it's still not enough, there must be new ways to do this. So this is how it will look. So this is your typical 8 Hz update rate. And as you can see, it's very precise. So still, it's everything lovely, plus minus 2 centimeters, but we specifically moved very, very quickly just to show that the distances between the dots may be comparable with their how curvy the path is. When I have a smooth track, like, I don't know, ellipse, it wouldn't be a problem. But when I have a sharp curves and sharp turns, then the update rate may be not enough. And the only way for the solution is to increase the update rate of the location system. What's the problem? The ultrasound propagates slowly. That's great because it helps our system to be so precise. Remember that speed of sound is around 340 meters per second. And the speed of light is 1 million times more. So basically it means that for radio-based, and we are measuring time of flight, but time of flight of ultrasound as compared to time of flight of radio. So for radio-based systems, it's effectively a million times more difficult to achieve the same accuracy. Of course, it's a very fundamental simplification, but nevertheless. So time of flight of ultrasound is the biggest asset when we talk about the accuracy, and at the same time is the biggest limitation when we talk about their update rate. Why? Now imagine that you have a large map, for example, 30 meters. So it means that their air, or let's say the time for the sound to propagate in this distance would be 340 meters per second divided by 30. So a gross maximum update rate that you can achieve without any other losses, time losses, would be around 11 Hertz, which is the maximum. But of course, on top of this, you will have losses due to processing, filtering, radio, etc. So effectively, on 30 meters, you would expect roughly 6, 5, 7, depending on the settings, depending on their which architecture you are using, but roughly that one. So loss about 50%, maybe 40%. So which is okay for the majority of industrial applications, because typically people say, okay, I want real time. How much? Okay, 1 Hertz, maybe 2 Hertz. That's great. So we typically talk about 8 Hertz for, let's say, typical submap, which is 10, 20 meters indoor. But for example, if you have a larger map, like 30 meters, so you'll have around 11 Hertz theoretical limit and 5, 6, 7 Hertz real practical. And if you have a very quick cart moving, that would mean that the dots come too rare, and if the object is moving too quickly, some data points may be simply missed. So it means that you have a curve, but instead of curve, for example, there's a curve, you have one location and another location, and this location you simply don't have it because it was so quick. If you have a smaller map, you may, purely based on ultrasound, achieve a high update rate. So we experimented in the past, and it was around 40 Hertz, like an absolute minimum, as we show here in ice hockey. Oh no, what's this? Air hockey case. So the size is just 2-3 meters, so you can get around 40 Hertz update rate, which is great for this simple case, but for the larger case, for example, karting, that would be not enough. Why I'm referring to karting? Because we have a couple of cases where people want, very quick movements, and they want a very precise track, basically in order to teach their players, drivers, how to drive properly. So our system is perfect for this because it provides their high accuracy of track, and now it provides a very high update rate, which is 100 Hertz, which is enough for even very fast moving mobile objects. And in order to achieve that, it's almost impossible to achieve by ultrasound, because once again, return back to the basic calculations. 340 meters per second divided 100 Hertz update rate, so the size of the map, even theoretical, would be just 3 meters, which is tiny. What to do? Sensor fusion is the solution. Sensor fusion is my personal favorite topic. It's an extremely complex thing, but it allows the best from both worlds. It allows high accuracy of indoor positioning system, and at the same time it allows very high update rate. It can be done even more than 100 Hertz from inertial management unit, from IMU. So let's talk about this deeper. But before we go there, what are the options? So basically there are three. Realtime Player, which is already available in the dashboard. It's IMU plus ultrasound sensor fusion post-processing, which we are discussing now in this video and in this presentation, and IMU plus ultrasound sensor fusion real time. It's a particularly complex topic. It will come later. It's not yet commercially available, but the first one, Realtime Player and IMU and ultrasound sensor fusion post-processing, is available right away. So what is Realtime Player? Realtime Player is basically a functionality inside the dashboard. It gets their location points, and then it does relatively complex interpolation inside by using algorithms, by using filtering, by using everything. So it tries to guess. Again, it's interpolation. Guess, not measure the location points. The result is pretty good, and it's suitable for relatively smooth curves. So when you don't have sharp turns or you have already sufficiently high update rate, Realtime Player is very good and is recommended. And it's great because it's already available. It's free of charge now, so you can basically use it right away and use it for the real-time data and for data that you already recorded, like in your log file. So use it, try it, use it. It's very good one. So let's check the performance. So this is the typical curve, and you can see these blue dots are ultrasound dots. We specifically and intentionally did it very quickly. So basically we jumped very quickly. As you see, their scale is 5 centimeters between their, so this is 5 centimeters. And again, there are just few dots, so 3 here because it already stopped moving, 1, okay, a few here because it was, then 1, 2, I don't know, 1, 2 here. And the track for Realtime Player is this pink one. Okay, the orange, we more or less reveal immediately what their IMU sensor fusion shows. So IMU sensor fusion obviously shows much better, but let's not touch that one. So the topic is blue and pink. So as you can see, Realtime Player is basically taking in some location points from the future in this case 0 from the future, and 5 points from the past. And then it's trying to put this information and place their basically interpolate using these points. So as you see, it's trying its best, but it's not perfect. In this case, it's slightly better because there are no overshoots, etc. But as you see, this is the biggest drawback of their real-time player, because it doesn't have this information. It doesn't have their acceleration information, unlike the IMU, which we will be discussing. So it's basically cutting the corners. It's making smoothing of these corners. So and it brings the errors. They're still not huge. So once again, this is 5 centimeters. So for example, this error is around 5 centimeters. But the problem is that you don't know in advance what will be your movement. So you cannot adapt this way or this way or this way. So what kind of filtering? So some of them are greater for this type of movement. Some of them give a better result for this kind of movement. But the logic is very simple. Real-time player is great. It's suitable for smooth movements because it makes it real 100 Hertz. Not real, but interpolated 100 Hertz. But in practice, it's basically helping as well. So it's not only producing 100 Hertz update rate and plays those locations, but it also does the filtering. So if there are some occasional jumps, so when there's a sufficient number of ultrasound points, it basically helps in all ways. So one is it increases the update rate. Second, it's filtering some occasional jumps or puts emissions on ultrasound. So if there was no location, for example, it will still work. And this is why this distance does matter. If I have a huge distance, then you would be able to, guess pretty well even 2-3 points or emissions on the location update of ultrasound. But at the same time, you will have more smoothing and your corners will be cut more and your error will be more. So there you can play with it and you can balance it. So for basic smoothing and for basic 100 Hertz, use Realtime Player. It's a powerful tool, is helpful. Again, it's post-processing, so it's not real-time from our perspective, because our real-time is basically 10 millisecond. But it's real-time, so you don't need to store the file and then play it. No, you can do this in real-time, but there will be latency. What latency? This is the latency. So effectively, your latency would be, in this case, 7 location update points. If you have 8 Hertz, so the latency would be around 1 second, roughly 1 second. But again, key point, it's available now. It gives 100 Hertz. It works very well for relatively smooth curves, and it's not costly. It's free now. So just another example for another sharp curve. You see it's more. It's making even a smoother curve, but cutting the corners even more. And you see, since it's expecting 3 forward points, but they are not available because, again, there was not available. So it means that it's another drawback of this. Typically, it's a minor drawback because I have much longer track, so it's typically not a problem. But nevertheless, pay attention that you will not be able to achieve the end of tracking unless you have sufficient points forward. So this is another example with rectangle. As you see here, you have relatively more dots, and so these are your blue ultrasound locations. This is your, you can call it ground truth IMU, resulting IMU, and this is your real-time player. Well, I would say good enough for majority of cases, because once again, it's really within 2 centimeters inaccuracy. But nevertheless, corners are kind of smoothened and error is here accumulated. But if you do it properly, you can use it. But once again, it was with this one forward 5 backward calculations. With this 3 forward and 5 backward, as you see, it's more smoothing, but the error is already somewhat 5 centimeters or more. It's nice. It's even closer to the reality when the curve is not too curvy, but the error in their corners or where there's a very quick change in direction becomes higher, and it will be high if you increase their let's say the order of their player. And this is a close look. Well, basically this is already 1 centimeter, so you can calculate roughly 5 centimeters error due to real-time player. But again, in these areas it helps a lot and it makes it even smoother, and the error is already lower. It's very difficult to calculate, but you can see it's basically reducing the jitter or spreads the jitter of ultrasound, making their location updates 100 Hz, and at the same time the spot smaller than 2 centimeters, so better than the original ultrasound. And I mentioned for smooth curves it's almost ideal. So as you see, I wouldn't guess which one is better. Is it real-time player or IMU sensor fusion? So use real-time player when you have smooth curves and you are okay with post-processing. Remember that it's all post-processing. You will have around 1 second delay or latency. The same, but slower moving triangle. It's already good enough. You see, over there we had just a few dots. I don't know, 1, 2, 3 dots per line. Here we have whatever 10 dots, and it's already good. Once again, this is 5 centimeters, so it's plus minus 1 centimeter difference from the ground truth, which is perfect. So again, the same conclusion. If you have smooth curves or you have sufficiently high number of ultrasound location updates, you can achieve even better results by using real-time player. This is why for example, in many of our robots and slow-moving videos, we do have real-time player enabled by default, because it basically makes much nicer, much more reliable and smoother track. But when all this is not enough, when you have a really fast-moving thing, when real-time player is not great, then there is a need for sensor fusion. Sensor fusion is extremely powerful, and sensor fusion, of course, is better than the real-time player, no doubt. Why? Let's talk first about the physical limitations. Physical limitation about ultrasound we already mentioned. So speed of sound is the greatest asset of system, because it allows very high accuracy of interpositioning system, but at the same time it's the main reason for a relatively slow update rate and limitation to increase this update rate further. So this is the physical limitation. And types of sensor fusion we already discussed. So it's real-time, which will come later. It's IMU sensor fusion post-processing. And today we will be discussing only about the post-processing, because we have it commercially, and this is exactly the video about this. So we're basically informing all our existing and future customers that this functionality is available. Please start using it. And the final and probably the most important reason is that sensor fusion in our system is done using IMU. Because sensor fusion may be done with many things. For example, in our robots, we do have sensor fusion between odometry, ultrasound, and IMU. We have in our Boxy robot, for example, also Intel RealSense, so a visual positioning system. So it can be sensor fused as well. So this is why it's my favorite topic, because you can achieve the best of the best by smartly, commercially, technically combining all this data together. because none of them are perfect. Every positioning system can have some limitations. For example, optical, light, too dark, too bright, some abstractions. Odometry, it may slip and it may calculate that it's moving, but it's not moving. Ultrasound, okay, ultrasound noise can block the system completely. In all cases, if radio is not available, you cannot get the data, you cannot update it, etc. So, but by smartly combining all this data and arranging self-checking, so basically sensor fusion, the best of the best from both systems, or more than one or more than two systems, can be utilized. So in our case, we are talking about IMU plus ultrasound sensor fusion. What is IMU? IMU stands for Inertial Measurement Unit. It, in our case, contains 3D accelerometer and 3D gyroscope. Each of our beacons, they have it already on board, so if you don't know, of course, use it. Let me highlight that when we talk about their IMU and positioning and why it's complex, we mean complex to achieve location. Angle, just raw angle data or measuring acceleration, it's nothing, so you can get it. It's a very, very basic functionality. But to measure the location using IMU is extremely complex task. To measure their absolute angle, it's also a complex task, but significantly less complex. But for that, you basically need two mobile beacons placed on your robot, and you will know location of your one of beacon and another beacon, and you know the direction where the robot is looking. Not the change of the direction, which you can achieve using only one one beacon, but static direction. We call this feature paired beacons, and we have it. So it's not a subject for this discussion. So we're in this video, just to make absolutely clear and sure, we are discussing about only a single subject, which is fast location measurement with 100 Hz update rate using sensor fusion between IMU and ultrasound. So what's the difficulty? The difficulty is in a double integration of acceleration. So the accelerometer data, if it was in, let's say, zero gravity, would be very simple, because we basically, integrate it, and that's good. Even the basic MEMS, so micro electromechanical systems, anyway, MEMS IMUs that are typical in your phones or in our beacons, they're good enough for this because they have low drift and etc, etc, etc. But low drift with zero gravity. When you have non-zero gravity, and obviously when we are on Earth, it's very difficult to subtract a huge acceleration that gives the Earth from the acceleration from the movement. For example, if you are just moving like this, you have nearly zero acceleration of your own movements. And at the same time, you have 1g acceleration to the Earth. And if you don't know the location of your beacon, or let's say not location, but the position of your beacon or crystal of your accelerometer, it's very, very difficult to distinguish between the acceleration caused by not properly aligning or by not knowing exactly their acceleration due to the Earth and your beacon's acceleration. It's very difficult, and the error is huge. And the result is very simple. Drifting becomes out of our plus minus 2 centimeter within a fraction of a second. Okay, if you calibrate it well enough, so it's around half of the second, sometimes 1 second. So within 1 second, calibrated beacon will drift away. So this is why purely based on inertial management unit, without any sensor fusion, without any cancellation of the drift, purely IMU-based systems, I don't know any of them really working. They are all using some sort of calibration. No, not calibration, some sort of cancellation of the accumulated drift. Because double integration obviously makes it very, very quick. So if in 1 second you have 2 centimeters error, then in 2 seconds you will have double of that, and double of that, double of that. So basically you are increasing very, very quickly, and in 1 minute your speed moving away, even though your beacon is, you know, standing still, would be, you know, meters and hundreds of meters in mathematics. So this is why drifting is the major problem, and you need to cancel it. And it's cancelled, of course, using our ultrasound, because ultrasound provides their absolute location. And by smartly combining, basically doing the sensor fusion, it's possible, and the result is the sensor fuse data, which is very accurate, because IMU provides no jumps, and IMU provides very quick 100 Hz update rate, and no drift, because the drift was cancelled using ultrasound-based system. Gyro drifts, of course, but gyro is a lesser problem. You need to very, very accurately know the angle in order to subtract their acceleration from their Earth, from your acceleration. But the drift of a gyroscope is less a problem, simply because it's less drifting compared to drift due to imprecise knowledge of crystal positioning, and we call it overfill of gravitation to their axis of accelerometer that provides drift. Once again, let me stress, IMU sensor fusion is a complex functionality, is really complex functionality. This is why, you know, it takes of time, but the fruits are, you know, perfect, because you really get the best of both worlds. Let me stress once again, IMU is perfect because there's no jumps like in ultrasound you can do. If you have non-line of sight, who cares? For some time. So it means that if, for example, something is obstructing the ultrasound, okay, IMU will not pay attention, and IMU will be still producing the location. And if after a fraction of a second or 1 second you are back to line of sight, then ultrasound will again correct it. And ultrasound corrects the drift, because there is all the time drifts of IMU, both accelerometer and gyroscope. And but it does it a few times per second, and to get the location data from their double integration of the accelerometer data, which is all the time corrected by the ultrasound data. So that's in short. It's a very powerful, very strong, and you get basically everything perfect. 100 Hz, you get additional robustness, and you get additional accuracy, because ultrasound obviously can jump plus minus 2 centimeters, but IMU doesn't jump. It has a noise which is a fraction of millimeters. So effectively you could achieve, if focus would be on accuracy, fraction of millimeter accuracy. It will be maybe in the future, it's not a subject for this discussion. But again, the best of both worlds is achievable. And the only drawback is complexity, which we solved for you. So this is once again our lovely track, very few location updates, and then you get the feature and apply their IMU sensor fusion post-processing, and it will look like this. So you can check and look at this. So this is wonderful. You can see how it was stopping, then many dots, because there's a momentum, more dots in this, and then there was again acceleration. You see there's acceleration, and then again sharp stops. So it's wonderful. You see there's a noise of ultrasound, so it's 5 centimeters, so I guess it's around plus minus 1.5, sometimes plus minus 2 centimeters. So we think there, but the resulting inaccuracy is even better than that. So again, you have the best from both worlds. You have high update rate, more robustness against abstractions, and even better accuracy. So IMU sensor fusion is very good. So once again, look at the corner. So you can play with it a bit later when you get the functionality in your hands. So let's look. This was one of those examples. So look, it's a very quick movement. So basically we did like this, very, very quick. And update rate was around 8 Hertz. So it meant that if you have 1, 2, 3, so I guess this was moved in 1/4 of the second, or maybe 1/3 of the second. So very quick movement. And yeah, you can guess that this is a triangle, but it's kind of very rudimentary triangle. By employing their IMU sensor fusion, you get pretty decent track, which is unlike Realtime Player, shows the exact ground truth. It doesn't have those limitations of the Realtime Player. So this is why when you have the most demanding, the quickest moving, then IMU sensor fusion is your solution. Now again, we already discussed for smooth, even Realtime Player is good enough. So for very smooth, you can easily use the Realtime Player if you wish. If you want for location updates, but if you want to get more robustness against, for example, abstractions, then IMU sensor fusion once again is your choice. Let's now talk about the post-processing time. Now, as I mentioned in the beginning, the sensor fusion that we have today is post-processing. So the location data is streamed in 2 ways to the computer. One is the typical way. So the mobile beacon is calculating, or the modem is calculating. Nevertheless, there is a ultrasound locations. Those do not change, the same. But at the same time, IMU from their mobile beacon has plenty of data, which is coming very quick, 100 Hertz update rate, and it's impossible to send it with typical radio channels because there will be not enough bandwidth, particularly when I have many mobile objects, for example, many cards moving on your track. So this is why to each of these mobile beacon there will be a modem and another modem, special modems. They are the same modems hardware-wise, but in terms of software, it's a special software that will be basically serving one purpose, taking a very fast data, IMU data, and sending it to a counterpart modem, and then it will be collected by the computer. So you'll have 2 streams of data. And these streams of data, they have, of course, timestamps. So this is why the sensor fusion algorithm is capable to combine the ultrasound data and IMU data, of course, with proper timing, and thus, after the sensor fusion processing, it's able to return perfect locations and 100 Hertz update rate. But it's post-processing, so it takes time. How much time? Now, I gave some examples. So currently, again, we didn't optimize this yet, but it will be optimized later purely by software. You don't need to change anything hardware. But today, as of now, a basic laptop, again, it's not a desktop, it's not something very special, it's not in the cloud, the very basic laptop makes the calculation with the following formula: 10 seconds plus T of drive, so how many seconds of log is recorded, multiplied by 0.12. So basically I have a half pipe jump or some BMX jump, which takes 5 seconds altogether. So then the processing time would be 10 seconds plus 5, so 10.6 seconds. So after you jump in 10.6 seconds, you have your perfect 3D track. If you have 15 minutes card drive, then it will be 10 seconds, 15 multiplied by 0.12, so resulting around 2 minutes. So after 2 minutes, after 15 minutes track, you will have your perfect less than 2 centimeters accuracy, 100 Hertz update track, which you can play, see the core curves, everything. And it's done on the basic laptop, as I said. So on the desktop, obviously it would be much faster, and in the future we believe that we will increase this speed of post-processing several times. But this is as of today, so just to set the expectations right. Let me one more time stress about what sensor fusion we are talking about, because we have several sensor fusions now, and we will have even more in the future. So there is sensor fusion for direction, and there is sensor fusion for location. Sensor fusion for direction, which is a part of our paired beacons configuration, that has been available for at least 2 years or something. So that's a complex task, but not as complex. Why? Well, because it's basically taking the location, and there's IMU, there's gyroscope inside, so it's not using the accelerometer, so it doesn't care about the drift due to accelerometer, and gyroscope drifts very little. But like all other sensor fusions, it takes the best from both worlds. Now, first of all, sensor fusion for direction returns also 100 Hz. Even today, so you already have it. So if you don't know, you have it already. So for example, without even the sensor fusion for location, so you have had it. So you had 8 Hz location update, but for direction you have 100 Hz. Where it's coming? It's coming from sensor fusion for direction. So once again, you have 2 beacons. Beacons are connected by 2 wires, so the data is streamed. One of these beacons is master. Master is calculating their angular position. Master is aware about their location, and master is capable to precisely sensor fuse their direction, which is calculated based on ultrasound, basically based on location of each of these points, and the IMU, in this case gyroscope. As a result, you have a very reliable internal direction. So it's basically coming from gyroscope, so it doesn't jump. At the same time, it doesn't drift, because it's constantly, the drift is constantly eliminated based on the ultrasound. So once again, the best of both worlds. No drift, 100 Hz, and very high accuracy and extremely high resolution. So it's fraction of degrees. But today we were talking about their location, sensor fusion for location, which is a new feature, significantly more complex feature, but very, very powerful, because, as I mentioned, it returns the best. 100 Hz, more robustness, and at the same time more accuracy, because it reduced their jitter of ultrasound location measurements. What's the future? The future is the holy grail, which is the real-time sensor fusion real-time. It's even more complex task, because as of now you've seen, so it takes us some seconds to post-process. We somehow need to pack it and to make it in real time. It's not an impossible task, but we are not there yet. The biggest benefit of that will be the low latency, because now we give you 100 Hz, we give you very high accuracy, we give you robustness, but the latency is seconds. So if you need, for example, to control your robot, if you need to stop very quickly, then we are not there yet. That requires a very low latency. Latency is the most complex task. It's solvable. It will be solved using the sensor fusion. It will be our future item, but not there yet. So just for you to know where we are coming and what you shall expect sometime in the future. Summary. Now let me just reinforce. So now we have several options. You have the real-time player, which is currently free of charge. You have the sensor fusion based on IMU. So IMU sensor fusion, it's available now, today. It gives you 100 Hz, the real 100 Hz, unlike the real-time player, which is interpolation. It gives you, at the same time, more robustness and more accuracy. And it's used for fast machinery, for quick sports, for very quick drones, for example. I'm sure you have many more other applications which we are not aware. And by the way, this project has been driven mostly by karting cases. This article and this video is related to the article which is already published on the web page. Check it. It's basically showing the same information but written. If you have more questions, don't hesitate to ask. We are happy to answer. Just drop us a mail to info@marmind.com. And thank you very much.